molecular beam epitaxy of 2D chalcogenides, and talking about the challenges and the opportunities that these materials present. So just so you know, I will explain what I mean by 2D chalcogenides as I go along, because I think at 2DCC we have a little bit of a broader picture of what that means than perhaps you might have in mind. So Kevin, this advancing thing is not working anymore. So just a second, guys. It's okay. Okay, so here's the outline of the talk. I'll first of all just go over the overview of 2DCC goals and facilities. And then I'll discuss what I mean by the chalcogenides that we're interested in. Because after all, as you might imagine, since we are a user facility, we can't be growing every possible chalcogenide on Earth. In an MBE system, we sort of have to make our choice. And so you'll find out what materials we're interested in. And they are sort of listed here. I'll talk about the MBE growth of bismuth and antimony chalcogenides. These are materials known as topological insulators. And the reason we fold them into the 2D chalcogenide family is that even though they are three-dimensional crystals, the states of interest are two-dimensional states on the surface. I'll also then talk about MBE of transition metal chalcogenides. And just as a word of caution, this is a field that we are certainly going to get into from the viewpoint of MBE growth, but we don't currently have any activities with MBE growth. Joan Redring and Josh Robinson do have programs going on in the MOCVD growth of these materials. I'll also discuss some other kinds of interesting chalcogenides that are particularly of interest to people like me who are in condensed matter physics, and these are superconducting chalcogenides. And finally, I'll tell you a little bit about the MBE capabilities, both current and future. And the current part will be folded into what I'm talking about in the beginning. So the motivation for the 2DCC, our two-dimensional crystal consortium at Penn State, is that we are interested in developing two-dimensional materials for next-generation electronics. Now, by 2D, we have a broad sense of the word. We are interested in certainly units, single unit cells, monolayers, surfaces also, and interfaces of chalcogenides. And these are all emerging as a compelling class of systems with which we can imagine doing new science and new technology. And some of the examples are given here on the screen. There is the plot that you see on the left at the bottom is a plot of from a review article by the group at Austin and others. It summarizes the characteristics of steep slope transistors built from various classes of 2D materials. And you see that TMDs and materials like bismuth selenide are promising. The middle plot is from some work that I had done with a colleague at Cornell, Dan Ralph. And that's a paper in which we showed that the two-dimensional states of surface states of materials known as topological insulators can be very efficient basis for making spin transfer torque devices for low power MRAM. And then finally, there's an example of hybrid two-dimensional devices that were grown and fabricated and measured here at Penn State by Josh Robinson and collaborators. And it's an illustration of how one might stack two-dimensional TMDs to make interesting devices, electronic devices. For example, resonant tunneling diodes with very large peak-to-valley ratios, even at room temperature. So the overview of the 2DCC platform is shown in this plot here. It's a combination of doing synthesis, hybrid MBE, chalcogenide MOCVD, and bulk growth, and that forms the basis of what we do. And then we fold into this characterization, which is in situ. So for example, STM, RPES, and 4-probe measurements of electrical properties, as well as Raman spectroscopy and photoluminescence. And then our theory colleagues here at Penn State and elsewhere are going to be collaborating with us in trying to guide the synthesis efforts by using fundamental, first principles studies in molecular dynamics, reactive force field methods, and so on, to help guide the synthesis and try to improve crystal growth in general. So there's a wide range of growth strategies that we are using here in the 2DCC for synthesis. As I'll describe to you later, we are interested in solid source MBE as well as hybrid MBE, MOCVD. So we go the whole span from chemical vapor deposition to physical vapor deposition. Okay. So what are some of the scientific goals of the 2DCC? Well, first of all, we are interested in developing the science of epitaxial growth of these 2T chalcogenides to a level where we can really establish materials that are comparable to what we can do with established classes of materials, like the 3,5 semiconductors, 2,6s, Feislers, oxides, and so on. And one of the primary goals is to figure out how we can develop wafer scale growth of electronic grade single layers and heterostructures of these 2D materials. So there's a whole class of problems that we have to figure out, right? Figuring out new growth approaches, combining this with theory simulation tools, and then in the end, if we can once we figure out how to improve these materials, we want to use them for scientific discoveries and technological advances. So what are the materials of immediate interest? Well, if you look at this table here, the selenides and tellurides and sulfides are certainly some of the materials that we are interested in generically. And there's the bismuth and antimony selenides and tellurides that we will be growing here at Penn State. We already are in an existing MBE chamber, and these are the so-called topological insulators. They can be three-dimensional in their crystal structure. So in other words, you can have a thick film, but the two-dimensional aspect is really at the surface. We're also then interested in this whole class of materials that have caught the attention of material scientists and physicists in recent years. These are the transition metal dichalcogenides, like tungsten ditelluride, molybdenum ditelluride, and so on. As many of you are aware, there's a great deal of interest in the basic optoelectronic properties of these materials. And then finally, there's also these very interesting classes of materials that maybe some people in this audience are not completely familiar with. And these are just transition metal monochalcogenide superconductors, so like iron selenide and iron telluride. As I'll show you later, these have some fascinating properties. I'll just give a very brief introduction to what's going on there. And then finally, what we want to also do, and we are currently interested in, is taking many of these materials and then magnetically doping them. So for example, if you take bismuth selenide and introduce a magnetic dopant like chromium or manganese or iron or cobalt, these have interesting properties. So it's a very broad sense of what 2D chalcogenides encompass. Now, let me start going through some of these classes of materials and first talk about the physical properties and physical phenomena in one class of materials that are close to my heart right now, that my group has been studying for quite a few years. And these are these materials known as topological insulators. And here, the 2D is really referring to the surface states. So the reason why these materials are interesting is because if you take a material like bismuth selenide or bismuth telluride, there's a very strong spin-orbit coupling that plays a role in determining the band structure. And if you combine this with fundamental symmetry, with the presence of time reversal symmetry, then this leads to states in the on the surface which span the gap of the semiconductor. And these states have a special property. Just like in graphene, the energy versus momentum is linear. So it's in other words, it's a Dirac-like dispersion. But furthermore, because of the spin-orbit coupling, it turns out that as you go around k-space, the spin and momentum are correlated with each other. So, to picture this in a cartoon-like way, if you look at the cube that's shown at the end, where I show electrons in a cartoon-like way going around different paths, you see that if an electron is moving in one direction, then its spin is predetermined. If you reverse the direction, then the spin has to reverse. So because of this sort of spin momentum locking, these types of materials are very interesting for spintronics, and we've shown that in recent studies. Furthermore, since these states are determined by the presence of some symmetry, it turns out that if you break symmetry, then you can get very interesting states like a quantum anomalous Hall insulator or Majorana fermions, which are of great interest to cutting-edge physics, which could then translate into interesting devices also at some stage. So these are, materials that are of great interest currently. We have an MBE system that currently is operating and growing these classes of materials. It's an MBE system that consists of two different ultra-high vacuum chambers. One is devoted to 3,5 semiconductors like gallium arsenide, indium arsenide, and the other one is really devoted to bismuth and antimony chalcogenides. So we've grown chalcogenide thin films on a variety of substrates such as gallium arsenide, indium phosphide, STO, sapphire, and so on, as well as a host of other types of substrates. And a big interest of ours at Penn State is combining these topological insulators with magnetism and superconductivity. So I just want to advertise that as part of the 2DCC, until our new chambers are set up for growing transition metal dichalcogenides by MBE, our current emphasis is in satisfying sample request proposals. You can go to mip.psu.edu. You can submit a request for samples, and the materials we're growing are sort of the ones that are summarized on the screen here. It also on the web we advertise the ones that we are capable of growing. And if you want to get a sense of what kind of physics can or science can come out of these materials, I've listed some of our recent publications over the last 4 years or so. So you can get a sense of what kind of physics you can pursue. One of the considerations, of course, in doing molecular beam epitaxy or epitaxial growth of any kind, conventionally, the idea has been that, well, you want to make sure that you choose a substrate which is lattice matched to whatever you're trying to grow on top. And so from that viewpoint, we've summarized over here the lattice constants of these common topological insulators that we're interested in, and some common substrates that we are interested in growing in, and other people have certainly used. We have used these substrates. And the conventional wisdom, of course, in the business of MBE or any kind of epitaxial growth, MOCVD and so on, is that you want to have a good lattice mismatch, a good lattice match with the substrate. Now, with these van der Waals bonded systems, so all of these layered materials, chalcogenides, they are unlike gallium arsenide or zinc selenide or silicon. There is van der Waals bonding between units of the lattice structure, and it turns out that really relaxes these constraints of lattice matching, but not, and sometimes in surprising ways. So, for example, let me show you an AFM scan of bismuth selenide grown on indium phosphide. If you look at the table here, you'll see that the lattice mismatch in plane is quite small. It's only 0.24%. Nonetheless, when you grow these materials by MBE on indium phosphide, you start getting these triangular or mesa-like structures on the surface. The surface is not perfectly smooth. On the other hand, if you look at the next image here, this is from a group at Rutgers, Sean-Chico's group, where they're carrying out growth of bismuth selenide on sapphire, and you look at the lattice mismatch on sapphire, and it's huge. Nonetheless, you look at the AFM of thin film of bismuth selenide grown on sapphire, and they can get very smooth growth. So clearly, this indicates that there is something we still have to learn here about what are the conditions that we want to use in order to grow these layered structures such as chalcogenides on different types of substrates. Now, we've been investigating MBE growth of bismuth and antimony chalcogenides on indium phosphide, gallium arsenide, STO, sapphire, and so on, as have many other groups. And to give you an example of the kinds of defects that abound in these systems, there are textured surfaces, there are twins, there are small grain sizes, there's extrinsic doping. And if you look, for example, at this AFM scan again, you'll notice that some of these triangles are, they have a different orientation from other triangles, right? And if you do X-ray diffraction scans, what you find is clear presence of twinning. So these AFM scans themselves give you an idea that there is twinning. And it turns out that if you look at these X-ray diffraction scans, you'll see that how you dissolve the substrate. When you dissolve the indium phosphide, if you do it under an arsenic flux or a selenium flux, that makes a difference in the in the kind of twinning that you get. So you can suppress twinning by doing the appropriate kind of desorption. So clearly, the chemistry, interface chemistry, when you nucleate on these surfaces and so on, does play a big role in what's going on. Now, we have been growing other kinds of complicated structures, complex structures on a variety of substrates also. So one of the big interests, as I'll show you why, is when you magnetically dope materials such as bismuth antimony telluride. And again, there is defects such as twinning, you get tilted domains, and we still need to understand how these magnetic dopants get incorporated. Are they clustered? Are they substitutional? Are they interstitial? And so on. These are all questions that are important from a crystal grower's viewpoint, and we've been investigating these in great detail. If you do very careful X-ray diffraction scans, so if you do phi omega scans or triple axis scans, you can learn a lot about how these twins are distributed in the sample. You'll find, if you look at the middle image, which shows this very interesting color plot, each of those curved red lines is essentially showing you how the omega scans vary as a function of phi and of the angle phi in the X-ray diffraction scan. And it shows you that there are different domains that are tilted in different directions. So these are all kinds of defects that we need to figure out how to get rid of. Nonetheless, if you do high-resolution TEM images of some of these doped samples, you find that when you dope bismuth antimony telluride with something like chromium, it seems to go in a fairly uniform way. We can't completely rule out nanoscale segregation, but it looks pretty good. So this is again giving you a sense that we can grow samples here. We can characterize these samples. All the characterization that you've seen, X-ray diffraction, TEM, has been done here at Penn State. And when there are sample requests, we can certainly make sure that these samples are carefully characterized. Now, these, why is it that growing these samples by MBE is important? Well, because you can get new physics out of it. So this is an example of a technique known as angle-resolved photoemission spectroscopy. And in this case, it's also got spin resolution, which is shown schematically by the arrows that are on top of the plots. What this is showing you is the energy versus momentum, in other words, the band structure of bismuth selenide films of different thicknesses. The QL corresponds to quintuple layer. It's roughly about a nanometer. And it shows you how the band structure changes as you go from 7 nanometers down to the ultra thin limit. And what you see is that at 7 quintuple layers or 7 nanometers, you get a Dirac cone. As you start making the sample thinner and thinner, the Dirac point is disrupted, and eventually a gap opens up. So this tells you that there's a quantum engineering possible of the surface states. This occurs because of hybridization, and it gives you control over spin polarization in the Dirac cone physics. And so from an MBE grower's viewpoint, the key aspect here is how precisely can we control these ultra-thin films. I've shown you these AFM images where you have textured surfaces. So what does it mean to have a 3 quintuple layer film? When someone doing ARPIS, this was our collaborator Zahid Hassan at Princeton and his students who took this data. But what does it mean when you take a 100 micron spot for an ARPIS measurement and you measure this very clean spectrum, and at the same time you have all these stepped surfaces? So these are important questions that we need to understand, and certainly we want to be able to grow really, really ultra-flat films. As I'll show you later, in the platform we are setting up here at Penn State, we will have in situ ARPIS available, so that after growing a film, we'll be able to go over to the ARPIS chamber and do measurements of this kind, not right away with spin resolution, but at least the energy dispersion curves, at low temperatures, in situ without breaking vacuum. You might wonder why we're interested in these magnetically doped films. It turns out that by magnetically doping topological insulators, we can get these exotic states, which are called quantum anomalous Hall insulators. This is a problem we are deeply interested in, and we are interested in figuring out how do we enhance the temperatures at which these exotic phenomena are observed. Currently, you need a low temperature dilution fridge or a helium-3 cryostat to see these kinds of phenomena. And what this plot here shows is that if you take a topological insulator, dope it with, in this case, vanadium, This is work that was done as a collaboration between a group at Penn State and a group at MIT. Then the Hall resistance is precisely quantized, and the longitudinal resistance is dissipationless. It goes to 0. Now, remarkably, and this is data that is from my group in a collaboration with a group at Princeton, we've shown that even though the best bismuth antimony chromium telluride films are highly, highly disordered, the best double crystal rocking curve widths are about a tenth of a degree, and the mobility of the electrons is only a few hundred centimeters square per volt second. Nonetheless, you can see extremely precisely quantized quantum Hall effect and a very small sheet resistance of just a few ohms. So the question is, from an MBE grower's viewpoint, if we have users who want to grow much more perfect films, how will the quantum properties of these materials evolve as we reduce the disorder? It's a very interesting question that we hope to address. Now, as I mentioned so far, I certainly, I'm straightforward about the fact that many of the topological insulator films that are being grown by my group, by other groups, we have a lot of problem with defects. So is there a strategy to actually reducing these defects, to growing really high quality materials? Well, some groups, and certainly this one group at Rutgers, has made enormous advances. And here is one way in which they've done it. So they use sapphire as their substrate. They, for example, deposit 3 quintuple layers of bismuth selenide. They then grow an indium selenide layer on top, and then they heat up their sample so that the bismuth selenide 3 quintuple layers, which is buried, apparently evaporates. They then grow a compound layer of bismuth indium selenide. And on top of that, they grow their bismuth selenide film. And when they do this, they get extremely good interfaces. And not only that, they have got the highest mobilities I know of, at least in bismuth selenide thin films, something like 15,000 or so centimeters squared per volt second at low temperatures, and they observe a integer quantum Hall effect. So this just gives you a sense of the kind of strategies that exist in the MBE world, and clever development of engineered buffer layers is certainly critical to advancing the crystal quality. Now, let me shift fields a little bit. In the remaining 10 or 15 minutes or so, I'm going to give you a quick run through of things that we do not currently do in my lab yet. So this is MBE growth of transition metal dichalcogenides. This is what we will be doing when we get our new MBE system. Now, until recently, there have only been a few reports on selective transition metal dichalcogenides, or TMDs. In the literature, and people in the field might correct me if I've missed something, but the structural quality is still unclear from the available publications. I have not seen, for example, double crystal rocking curves or phi omega scans and things of that sort. The grain sizes seem to be very small. Nonetheless, there's been some beautiful work coming out from a number of groups. This is an example of work from Hinkle at UT Dallas, showing some in situ STM measurements, showing ex situ transmission electron microscopy, as well as read measurements. Clearly having these in situ real-time probes are going to be very important to try to understand how the growth can be improved and understand the details of the nucleation and the growth kinetics. Another example in the TMD field, and just to give you some sense of how quickly this field is rapidly progressing, this is some work that is on the archive from another group in Texas, but this time at Austin. This is Emmanuel Tutuk and Sanjay Banerjee's group. They've been growing molybdenum ditelluride on sapphire. You get very nice read patterns. The read patterns, of course, the streakiness shows you that you have a disordered surface, but it's relatively smooth. And they show nice X-ray diffraction. Again, overall, I think this field is still just starting out, and we need to understand what the capabilities are going to be. One of the big advances made recently in the literature is this beautiful paper from Cornell and Notre Dame that shows that just as superlattices were developed in semiconductors, in the semiconductor world for many, many years, many decades, that one can at least have some expectation that we should be able to do this with MBE. And the results from Cornell and Notre Dame clearly show that even though there is still imperfections. There's, the interfaces are wavy and things like that. But nonetheless, people are starting to get a handle on how to make complex superlattices with these TMD materials. And they've actually explored quite a range of different combinations that I've listed here on the slide, anything from bismuth selenide, molybdenum diselenide to, molyselenide, molytelluride kind of superlattices. So again, this is, I've just shown you a few representative examples from the literature. There are several others, and obviously I don't have time to summarize everything, but it gives you some idea of the fact that this field is starting to boom, but defects are still a big issue that we need to deal with, both in the bismuth and antimony chalcogenides and also these TMDs. Now, just to whet your appetite in in a direction that is perhaps of more interest to physicists right now than the materials community at large, but there's a really enticing and exciting result that came out from China, from Shanghai, Jiaotong, over the last couple of years. And what this group has found is that if you deposit a single unit cell of iron selenide on strontium titanate, then by doing an in situ measurement of the electrical resistivity or electrical resistance, a 4-probe measurement, without taking the sample out, there seems to be very intriguing evidence for superconductivity at around 100 Kelvin, perhaps a bit higher. This is really, really exciting because there's a number of questions, fundamental questions that come up. What determines this DC? What are the upper limits? Why is the STO important? There are experiments that have followed up on this from Stanford and other places. I haven't summarized all the literature here, but just to give you a sense that ultra-thin iron selenide is going to be at the top of our list for the kinds of problems that we're interested in. It turns out that iron telluride also has some interesting aspects of superconductivity when grown in particular kinds of heterostructures. So I think this gives you a sense of what is the range of materials that we are going to be aiming at. And now I want to give you a sense of how we are going to be doing it. So I mentioned that we already have an MBE system, but the materials in this MBE systems are sort of locked into place. They're the bismuth chalcogenides. I don't think we can expand that family very much in that existing MBE chamber. With the new MBE chambers, we're going to have 2 new MBE chambers. One is going to be located in the Millennium Science Complex where I'm giving this talk. This is run by Roman Engel-Herbert, who is a professor of material science and engineering here at Penn State. And he currently has an oxide system. He's in the process of designing and ordering a hybrid chalcogenide MBE system, which should be delivered in 2017, and it'll hook up to the oxide chamber. There will be a UHV vacuum shuttle that will connect to this chamber so that we'll be able to transfer samples out of here into another chamber that I'll tell you about shortly. One of the unique aspects of this particular MBE system that Roman is setting up is that the sources are going to be metal organic. So this is going to be hybrid chalcogenide MBE. And the reason for doing that is because we want to play around with the nucleation and growth kinetics. And it turns out that our theory colleagues who use reactive force field methods have ways in which they can actually help us figure out what are the right precursors to use. They can do modeling and hopefully guide the synthesis program in a positive direction. The other system that we are setting up is a growth and characterization cluster, and that's going to be set up in a different building. It's in the physics department. This has already been ordered, and the system is currently under construction. It's made by Sienta Omicron, and it consists of 3 primary units. One is the EVO50 2-inch wafer MBE system. Another is a cryogenic ARPES system, and then there's a cryogenic LT nanoprobe from Sienta Omicron also. This has an SEM in it, and it allows you to guide 4 STM tips onto a sample surface, and you can do 4 probe measurements as well as spectroscopy currently with 1 tip, but in the future you can do the scanning with all 4 tips. That's when we put that into place. Some of the specifications of these systems, the thin film MBE system is going to have a 2-inch wafer MBE. It'll have an adapter for smaller centimeter squared substrates so that we can go into the CN to Omicron, STM, and outpace chambers. It'll have a cracker for the selenium. It'll have an E-gun source, effusion cells, and either a banded system for substrate temperature and control or an ellipsometer. We still have to decide which one we want to put into place. The STM is, I think, a unique capability here because we'll be able to do cryogenic scanning tunneling microscopy as well as 4 probe measurements. And it comes with an Orsay Vortex SEM column that allows us to guide and position the tips. And the base sample temperature will be in the liquid helium range. There's a very small superconducting coil that that's going to be in place for doing certain kinds of measurements. We can't have a big field because there's this ARPIS chamber right next to it. The cryogenic ARPIS, again, can go down to low temperatures, down to about 20 Kelvin. We have a helium UV light source, and it's the monochromator is optimized for helium-1 and helium-2 excitations. It's got reasonable energy resolution, and this should allow us to really map out band structure of a variety of interesting materials that we grow. So I think this is it's a very powerful combination of characterization and synthesis tools. Once these different tools come online, users will be able to submit proposals for coming in and learning how to use these tools. We have research scientists in place and postdocs who will be working hand in hand with users, much the way that when you go as a user to any other national facility like the National Magnet Lab, or you go to a synchrotron, it's going to be the same mode of operation here, right? You'll be working hand in hand with the technical staff here, and users who become proficient enough to an expert enough in these instruments can then come back and may well be allowed to to run these tools by themselves. So I hope I've been able to convince you that MBE of chalcogenide thin films broadly offers many new challenges to the science of crystal growth. And regardless of the beautiful physics that we are seeing in many of these materials, it's quite clear to us that controlling defects is still a very, very big issue. These materials are nowhere near the quality of MBE grown gallium arsenide or indium arsenide or silicon or zinc selenide or mercury telluride, and we still need to figure out how to do this. And this is what we hope to make a big impact on in this field. And we hope that there's going to be a powerful platform here for users to come in and solve these problems. So I thank you very much for the attention, and I'm happy to take questions.
So thank you everyone for attending. Right now we'll moderate through the questions. I see one question in the chat box, and then can you just read it out loud? And
sure. So this is from Suresh Vishwanath at Cornell, and his question is, how is the flux measured for the E-beam system? Any N-type dopants for the TMDs? What are the substrate preparation facilities available? And why is there europium sulfide in the source list? So let me start at the bottom. So europium sulfide is because it's a very interesting ferromagnet, ferromagnetic insulator, and there's been some intriguing studies from MIT in combining europium sulfide with topological insulators. There's some interface-induced magnetism. Substrate preparation facilities, I'm not sure what you mean by that. We do have a bulk crystal growth program. But other than that, I think we just have standard substrate preparation. So I'm not sure what you mean by that. N-type dopants for the TMDs, we really haven't thought about that yet. But I'd be happy to get any suggestions. And the flux measurement for the E-beam system, I have my research scientist here. So yeah, so we have, but we don't have anything specific for the E-gun itself. I mean, I think that's what he's trying to get at. I mean, the MBE chamber itself has a quartz crystal monitor, and it also has a beam flux monitor, but we don't have anything specific for the E-beam.
Suresh.
Sorry, so there's a question from Rafael Jaramillo. What metal organic precursors will be used for the refractory elements in hybrid MBE? I don't have Roman Engelherbert in the room here. I know that he is looking at a variety of precursors, but maybe one of the other postdocs here have you heard recently what he's decided on? Or so I'm sure he'll be happy to answer that question if you email him. I don't think he's settled on what specific precursors he's going for. And then there's another question from Suresh. I think skipped something. It says, I mean hydrogen plasma high temperature anneal. Oh, the substrate preparation. Okay. Yeah, so it'll just be annealing. We don't have a plasma in there.
Hydrogen plasma is something we might add on the extras.
But do we have a flange for? Do we have a flange for that?
Potentially, but it's
So potentially we might have the hydrogen plasma, but at least it's not in the immediate plan.
yeah. The substrate temperature I think will go up to 1100 C.
Okay, so in case you didn't hear, this is Anthony Ricciardella, who's the research scientist who's in charge of the MBE system. The substrate temperature will go up to 1100 centigrade. Any plans for introducing tin into the MBE system? Again, Suresh, you do MBE, so you know how difficult it is to put every element that you want. I would love to, but I think we're going to have to make choices. And again, the materials I listed for on that slide were our initial plans, but we may change those as we go along. We have some high temperature effusion cells, low temperature fusion cells. We have the E-beam, so we'll have our choice, and it sort of depend on what we think is the most interesting science to pursue. Are any of the sources retractable? We didn't make plans for that. No. So no. I think that's possibly what the next question is also asking, whether they're load locked. And again, I think the crackers, the selenium cracker, trying to remember if no, I don't think so. So we didn't plan for retractable or load locked sources. Again, to give you some sense, with my current MBE chamber, which is an EPI 620 and an EPI 930, I mean the 3.5 chamber, we don't really open it up that often, maybe twice a year. And the bismuth chalcogenide chamber, we open it up and we are back in business within 10 days, So I'm guessing this is a smallish chamber, and I think we'll be able to, if we do have to vent, getting back to business is not going to take that long. Anyone in the room wants questions?
Yeah, so while we're getting more questions in the chat box, does anyone in the room have any questions for Nitin?
We're talking about that buffer layer engineering where
Yes.
they deposited the low temperature bismuth selenide. What is the role of that? I mean, do they do the low temperature increase temperature for deposition actual growth? Is that
Well, so the question here was, I gave the example of Seong-Shi Ko's, engineered buffer layer, and the question is, why do they, what is the role of that buffer? So from what I understood from the paper, I haven't really talked to Sean about this, is that the indium selenide itself gives you a really good surface to grow bismuth selenide on top of. But they can't grow the indium selenide directly on sapphire for some reason. There's some funny chemistry that occurs there. And so they seed the growth of the indium selenide on a very thin layer of bismuth selenide. And surprisingly, and I don't know whether this is, I think it's not speculation, they have clear cross-sectional TEM images. When they heat up the bismuth selenide indium selenide combination, the bismuth selenide apparently just diffuses through and evaporates. And that leaves this indium selenide in a fairly good crystalline form on the sapphire. And that provides then the basis for growing the rest.
So, I mean, I don't know if it's there in the paper. Have they tried depositing indium selenide at low temperature and heating it up?
I don't know that they tried. I honestly don't know. I don't think they mentioned it in the paper. So there's a question here. Will there be, let's see, which one should I go first? Is it Brian?
He's the next.
Okay, is one vacuum suitcase design compatible with both of your MBE clusters? And the answer is yes. So the MBE system that Roman is setting up, he is designing it so that it'll be compatible with the with the Cyan to Omicron transfer system. Suresh asks, will there be technicians to assist with the STM and RPS if we just do the growth? Yes, the technician in this, so Anthony Richardella, who is a research scientist at the Materials Research Institute here, is part of the 2DCC, and he will be, he has a lot of experience doing very high quality STM with, he was Ali Asghani's graduate student many years ago. We also have a new faculty member joining. His name is Chuezu Chang, who discovered the quantum anomalous Hall effect. And Chuezu is an expert on RPES, so he will be our advisor on the RPES system. Anthony and I have both, closely collaborated with people who do RPES, like the Princeton group. And so we are familiar with the physics of RPES. Neither of us have actually done RPES measurements before, but Chuezu has, and he will be our colleague here. The tellurium system, what's that? Yeah, we don't have a cracker for tellurium. We currently use just an effusion cell for tellurium, and we haven't had an issue with that. Frankly speaking, I was a little bit worried about even using a cracker for selenium, because when I did this, when I first got in the MBE business of 2.6s, and I tried using a cracker, it started eating up. It started corroding the inside, seams and wells in my MBE system. But I've now heard from multiple people with these crackers, and that it's okay. So we're using the cracker for selenium. There is a group at Delaware, Stephanie Law, who has shown that when you grow bismuth selenide with cracked selenium, for some reason, which I don't completely understand, the surface states are more robust with respect to exposure to ambient atmosphere. I don't quite understand that, but it seems to be a solid result. So cracked selenium may have a big advantage. I don't know that cracked tellurium necessarily does. Selenium comes off as very long chains, and you can imagine that that really has an effect on the growth.
So maybe we have time for one more question or two more questions, and then we'll wrap up for the day.
I see that someone is typing. I see. Okay, that's an interesting. So Suresh is pointing out that tellurium and molybdenum have an electronegativity that's very similar, and so they don't really like to bond, and that's what his question was. Okay.
So we have Raphael and Brian yet, and then I think we'll close up the webinar.
Brian's question is, are the other MBE systems of campus, such as the Gen 930 on the left, also going to be user facilities? So well, it's an EPI 920 and 930 and 620. Those are I am offering those for sample growth, not as a user facility in the sense that people come in and use the system directly. And this is because, you know, I have my own research program to run, and that is what, so a fraction of the time of that system I'm certainly offering for the 2DCC. So currently, we have a few user proposals that have come in, and we have, you know, we will be growing samples that were requested. The sample growth is done completely free of charge. You know, you do have to just go in and submit a proposal, and we try to find an appropriate timeline to get that done. Raphael is asking, any interesting strategies to increase adatom mobility of these refractories? Haven't really thought about that. You know, it's certainly a question that that is worth discussing in the community. What's that?
The hybrid system.
Well, I think he's probably so suggestion came from the audience is that, well, Roman is planning to do hybrid MBE anyway, which presumably will change you know, some of this kinetics at the surface. But other than that, we don't have any ideas in mind. Now, you know, many years ago in the 2,6 MBE business, I recall that in mercury telluride and cadmium telluride growth, there were groups that had tried to use laser-assisted MBE. I mean, I should go back into the literature and look to see whether it actually made any difference or not. But at this point, I don't have any really clever ideas for increasing the mobility of the refractories.
Any last questions before we close up? We'll give you a few seconds here to enter them.
Okay, if not, you know, thanks very much for listening. I think it's the first time I've given a webinar, and the question and answer session has been very, you know, very productive. It's great. Thank you very much.
Yeah, so the next webinar will be on September 27th, and again, the time will change now. We'll have them at 12:30 to 1:30 going forward, Eastern Time. Basically, they're advertised about 2 weeks before they start, and so just as you did this time, you can register online, and then you get a unique link to join the webinar. Thank you, everyone, for coming, and we'll see you next time.